Chemistry of Life, Part 1, The Nature of Matter. Matter is anything with mass and volume. Volume is the amount of space an object takes up, and mass is the amount of stuff in an object. All matter is made up of elements, and each element has its own unique type of atom. If you look at the major elements that we'll be looking at in biology, they're all right here. You can see that carbon, hydrogen, and oxygen are the three main ones that we look at. And if you look at the human body, for example, you can see that that makes up more than 90% of us. We also look at nitrogen and phosphorus, especially with proteins and nucleic acids. So these are the 5 elements that we will be focusing on in this class. Here's another look at that. You can see some other trace elements that make up living things. Everything in the universe is made up of atoms. Atoms are the smallest unit of matter that you can have that cannot be broken down by chemical means. Atoms are made up of 3 different parts: protons, neutrons, and electrons. Protons have a positive charge and a mass of 1. They're found in an atom's nucleus. Neutrons have a neutral charge and a mass of 1. They're also found in the nucleus. Electrons have a very, very small mass, so small that we don't really count it, and they're found outside of the nucleus in an area called either the electron cloud or in energy levels. And here you can see the electron cloud on the left and the energy levels on the right. We'll be using the model on the right in this class. The atomic number is a number of protons in an atom. Now, the number of protons is also usually the number of electrons, unless you're told otherwise that's the case. The mass number of an atom is the number of protons plus the number of neutrons in the nucleus. And the atomic mass is a weighted average of all of the mass numbers of an element's atoms. So the atomic mass takes into account all of the atoms of any particular type of element. There are some elements that have multiple versions of the atoms because they have different numbers of neutrons, and these are called isotopes. Isotopes are atoms of an element that have the same number of protons but different numbers of neutrons. They tend to have the same chemical properties because they have the same number of protons, which means they have the same number of electrons, and it's the electrons that determine the chemical properties of an atom. But the ones with greater numbers of neutrons tend to be unstable. And the fact that they're unstable can be used because unstable atoms will tend to break down into more stable forms. Those that are radioactive give off high energy, which can be dangerous to people. Here we have 2 isotopes of carbon. On the left you have carbon-12, on the right you have carbon-14. Carbon-12 has 6 protons and 6 neutrons. Carbon-14 has 6 protons and 8 neutrons. Their chemical properties are the same because they have the same number of electrons, but carbon-14 is unstable. So it actually will break down into a more stable element over time. In biology, we use isotopes mainly for figuring out how old things are. That's with radiometric dating. And then we can also use them for diagnostic processes. Well, the electrons are the part that we really focus on mostly because the electrons are the parts of the atoms that determine the chemical properties of the atoms. And the electrons are arranged in places called energy levels, and these energy levels surround the nucleus. There are many different energy levels that surround the nucleus. The first one can hold up to 2 electrons, and all the rest can hold up to 8. Now, the electrons are in the outermost energy level, which has electrons, and I'm going to say that again. the electrons that are in the energy level, the outermost energy level, that has electrons, those are called valence electrons. If there's an energy level outside of that that doesn't have any electrons, it doesn't count. So atoms are most stable when this outermost energy level with electrons, this valence energy level, is full. And again, the first energy level can hold up to 2, and then it's full. And then all the rest can hold up to 8. Once you get to 8, it's full. So if you add another electron, you're going to start filling another energy level outside of the one that you are currently in. Here you can see 4 different elements, and you can see the number of electrons in their valence energy level. So for example, hydrogen has 1. That first energy level can hold up to 2, so it could add 1 more. Oxygen has 6 in its outermost energy level. It could hold 2 more. Nitrogen has 5 in its outermost energy level, so it could hold 3 more. And carbon has 4 in its outermost energy level, so it could hold 4 more. Well, because atoms want a full outermost energy level, what they will do is they will form bonds to form compounds to get a full outermost energy level. They want that valence energy level to be full. Once they're full, they become unreactive or inert. That's what the noble gases are. We can look at the periodic table of elements to see the chemical behaviors or chemical properties of the different elements based on their valence electrons. So on the right, you have all of the noble gases, and they are inert because their valence energy level is full. They don't need any more electrons, and so they will do nothing. They have no chemical properties that are reactive. All the others, though, are not stable, and so they are more reactive. For example, lithium, which you can see in the first column, has 1 valence electron, and so it's very unstable. It really wants to get rid of that 1 electron. It could add 7 more, but it's much harder to get 7 than it is to get rid of 1. So those in the first column, except for hydrogen, will all try to get rid of their electrons. Hydrogen can't go down to 0, so it's going to have to pick up 1. So compounds are what are formed when atoms combine to fill their valence energy levels. And what the atoms do to form their valence energy level is to form bonds with one another. So if we look at this example, we have sodium, which is actually a solid on the left. It will combine with chlorine, which is a gas in the middle, to form sodium chloride. That's a compound. Notice that the sodium chloride is nothing like the 2 things from which it's made. One of the things you're going to need to be able to do is to read molecular formulas. And so we have 3 examples here. Notice you have glucose. Glucose has 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. Whenever you see a subscript, the subscript tells you how many atoms you have of that element in the molecule. Ammonia has 1 atom of nitrogen, 3 atoms of hydrogen. Now, when you see a coefficient in front, like we have with water here, we have 3 molecules of water. Each molecule is made of 1 oxygen atom and 2 hydrogen atoms. So that gives us a total of 6 hydrogen atoms and 3 oxygen atoms in 3 molecules of water. So you have to multiply the coefficient times the subscript. And remember, if there isn't a subscript, it's implied to be 1. So when atoms combine to form compounds, it involves a chemical reaction. When you have chemical reactions, it's important to remember that both mass and energy are conserved. We call this the conservation of matter and the conservation of energy. And the way we show the conservation of matter is through balanced equations. Now, when we look at equations and we look at chemical reactions, you should know that some reactions happen very quickly, for example, an explosion, while others happen very slowly, for example, rust. Rust takes a long time to happen. When you look at a chemical reaction, the things to the left of the arrow are called reactants. The arrow means to form, so the reactants form the products. You begin with reactants, you end with products. So in this example, you can see that we have 2 molecules of hydrogen combining with 1 molecule of oxygen, and that will produce 2 molecules of water. If you count the number of atoms in the reactants and the number of atoms in the products, you'll see that they are the same. That is conservation of mass. Photosynthesis is a great example of a chemical reaction. We'll look at photosynthesis a lot this year. Living things rely on chemical reactions to get things done and to stay alive. So we're going to be looking at a lot of different types of chemical reactions that living things use. Now, when you have a chemical reaction, you can have a chemical reaction that takes energy in, or you could have a chemical reaction that gives energy off, or you can have the type that actually store extra in the bonds. Let's take a look at these. Reactions that release energy, think again of an explosion. These a lot of times don't need any help to get going. Those that take energy in will always need help to get going. So we have building reactions and we have tearing down reactions, basically, is what we're looking at. Now, all chemical reactions require some amount of energy to get started. And this energy that you need to get a reaction started is called the activation energy. And it can come in a variety of forms. It can come from sunlight. It can come from friction. It can come from really anything. An example that you're probably familiar with is a fuse and like a firecracker. The fuse is lit. The heat going in on the fuse is the activation energy to get the reaction going. The reaction would be when the firecracker explodes. In this example, you can see the bear is going to push that big rock down the hill. When the bear pushes the rock down the hill, the rock will end up with less energy than it had before. It's going to be converted from energy of position to energy of motion, and then it will stop. So we have the starting substance at a higher energy level than the finished. So this is the energy that is given off. Notice there's a little lip of rock right here, and that little lip of rock is the activation energy. So you need some kind of energy to get the thing going. Once the reaction's going, it just goes. So here we have the reactants on the left, the products on the right, and in this example, we have energy that's been given off. Remember, not all reactions give off energy. Some of them actually take energy in. Here's one where energy is being given off. An example here would be like a heat pack for your gloves in the wintertime. If you shake that up, that's the activation energy, and then it will give off heat. That's energy being given off. That's this type of reaction. The other type of reaction is where energy is absorbed. This is an example of a cold pack, where you shake it up and it becomes cold. The reason it feels cold to you is because it's actually absorbing energy from your body. There are 3 types of bonds that we'll be talking about in this class this year. The first 2 are bonds between atoms. The last one is the weak chemical bonds. These are bonds between molecules. So the first 2 are bonds between atoms. The last one, bonds between molecules. Ionic bonding is bonding where one atom will give electrons to a different atom. When an atom gives away electrons, it becomes positive because it has more protons now than electrons. We call these cations. When an atom takes electrons from another atom, it will have more electrons than protons, and it becomes an anion, and it's a negatively charged ion. Well, these behave like magnets. So a cation is attracted to an anion, and that will hold them together in an ionic bond. So here you can see an example of this. Sodium has one valence electron. That makes it unstable. It wants to get rid of that valence electron because if it doesn't have that one valence electron, then that energy level doesn't count, and the next one inward actually has 8. So it will give up that electron. By giving up an electron, it becomes positive. It's a cation. Chlorine, on the other hand, has 7 valence electrons, so it just needs one more to be stable. So it will happily take that electron from sodium. In the process, it has more electrons than protons and becomes an anion. Again, opposites attract, and so they're held together in an ionic bond. We call compounds that form from ionic bonds salts, and they tend to form crystals. Here's a sodium chloride crystal. Again, sodium is now a cation, chlorine is an anion. The other type of bond between atoms is a covalent bond. Covalent bonds form when atoms share electrons. So here's hydrogen. Remember, hydrogen has just one valence electron. It needs 2. It can't get rid of its only electron, so it's going to have to pick one up. So the way it will do that is by sharing with another atom that also needs an electron. And luckily for hydrogen, it's the most common element in the universe, so it can find another hydrogen atom to form a hydrogen molecule. They're each sharing the electrons that they have, so 2 electrons are being shared total, and each one can claim to have a full valence energy level. It's kind of like, think of where you live. You are sharing that place, you're sharing your home. It is your home, but you're sharing it, but you can say it's yours. When atoms form covalent bonds, they form what's called a molecule. So when you see the word molecule, that tells you that there are covalent bonds inside of there. They're sharing. You can see that. Notice in the upper right-hand corner of this example, oxygen is actually sharing 4 electrons, so it forms a double bond. A single bond is sharing 2 electrons, a double bond is sharing 4. So we have there. And you can see another look at it. These are all examples of covalent bonds forming molecules. Now, we're going to be looking a lot at water. This is water here. And notice the shape of water. That's important. It's not shaped linear, so it's not a straight line. It's shaped at 90 degrees. So remember that. That will be important. Here we have methane. It has what's called a tetrahedron shape. So we get to the point where we talk about electronegativity. Now, electronegativity is how strongly an atom can hold on to its electrons. So they're not all the same atoms in their ability to hold on to electrons. Some atoms are better able to hold on to electrons than others. If an atom has a high electronegativity, that means it has a strong ability to hold on to electrons. So we're back to water, and remember the shape of water. The red here is the oxygen atom, and then the gray, those two are the hydrogen atoms. Oxygen has more electronegativity than hydrogen, so oxygen is better able to hold on to the electrons. Because of that, the electrons tend to cluster on the oxygen end of the molecule. So you end up with a negative end of the molecule and then a positive end down here where the electrons are not as concentrated. So you have a positive end with the hydrogen, a negative end with the oxygen. That results in a polar molecule, a molecule with a positive pole and a negative pole. So this is what happens when you have atoms combining with different electronegativities. That's not always the case. For example, methane is nonpolar because it's surrounded, that center carbon is surrounded by the hydrogen. Water is polar, and so it ends up with a positive end and a negative end. And that's the result of unequal sharing of electrons. Sometimes it'll be worded as an unequal or uneven distribution of electrons. So unequal sharing or an uneven distribution of electrons causes a molecule to be polar. When you have one polar molecule next to another polar molecule, what ends up happening is the molecules will arrange themselves so that the positive end of one of the molecules will face the negative end of the other. And this forms a weak chemical bond, commonly called a hydrogen bond, also called van der Waals forces. So van der Waals forces are the same as hydrogen bonds or weak chemical bonds. And all of that describes when polar molecules are attracted to one another. In nature, we see this as one reason the gecko is able to climb up a wall, because it takes advantage of these weak chemical bonds, these hydrogen bonds, to cling to the surface. So we're going to use hydrogen bonds and van der Waals forces interchangeably. I'll typically call them hydrogen bonds. Now, depending on what college you go to, sometimes they just call everything a hydrogen bond. And so that's kind of what we do. Some colleges will actually differentiate between the two. Typically, if you want to know the specifics, a hydrogen bond is when only hydrogen is involved. But again, it kind of gets used as an umbrella term. So here we can see water being attracted to ammonia. It's the positive end of the water, the hydrogen end, that's being attracted to the negative end of the ammonia, which is the nitrogen end. That is a hydrogen bond. Now, one single hydrogen bond is actually very weak. But when you have trillions of these molecules together, for example, in a glass of water, it actually can be strong enough to give you a surface and a surface tension. And think about how insects can walk on the surface of water. Some insects can. And that's the result of the hydrogen bonds.